As you study calculus, throughout the course, you will encounter certain big theorems of calculus. They're called big theorems because they're really important. They're like, monumental accomplishments of the human mind as we try to make sense of what calculus is all about. Well, there are these theorems that are along the way that really emphasize what calculus is all about. And yeah, so that's why they're called big theorems. And one of those big theorems is the intermediate value theorem. And it's often abbreviated IVT, right, for obvious reasons. So IVT, intermediate value theorem, what is it all about? Well, let me introduce this by a game, right? So now, to play this game, we need graphs of functions, right? So, you talk about graphs of functions and sign me up for that game. But let's say so I'm going to draw a few functions. Let's say like that one. And let's say like that one. Oh, can't have two shaded in circles there. Nope, because that would fail the vertical line test, and then I can't call it a function. Let's say that one there. And let's see if we can squeeze one over here. And I'll even have this one, let's say, like this. And then like that. All right. And then I'll put one down here kind of in the middle. And let's say this one is like that. All right. Okay, so these are our functions. These are all graphs of functions. And here's the game. You get to pick a y value, so a value on the y-axis. And then I would have to find an x value so that when I plug it into the function, this side, I will always get the y value that you picked, right? Let me say that again. So here is the game. We have the graphs of these functions. Player 1 gets to pick the y value. Player 2 has to find the x value that when I plug it into the equation of my function, I will get that y, right? So it's almost like you're working backwards, because normally when you talk about functions and you talk about the input and the domain, well, you start with values in the domain, evaluate your function, and then you get values in the range, right? But now what we're saying is pick a y value here, any y value you want, and then the other person has to find an x that when you plug it into your equation gets you that y. So my question to you is, let's say you are the person that has to find the x that goes with the y. Which of these functions would you want to use, right? In other words, which of these functions do you think will guarantee that you will always be able to find an x to go with the y, right? Well, if I were you, I would choose this one. I would choose this one down here. And here is why I would do that. So for instance, there might be several ways that the other person could win, or there could be just one. But for instance, if you were to pick this one, right, and the first person gave you that y value, let's say that was like your y0. Well, there is no x at all that when I plug into this function, it would give me this y, right? So yeah, the whoever, if the person picked this y value, they would win because you couldn't find an x that would work, right? If this is the function that you're playing with, then you're in even bigger trouble because they could pick anything, let's say, not including this one, so I'm going to use a parentheses, right? Up to this one, I'll use a bracket like that. So any y value in this range, right? Well, technically it's not in the range of the function because if I try to draw a horizontal line, no horizontal line in this range will touch the graph, right? A point on the graph. Right? So yeah, this one, the person basically, they would only have one special value that they could choose to guarantee their win. Here, they would have a lot. In fact, infinitely many. There are infinitely many numbers in this interval, right? In fact, as far as the real number line is concerned, every interval on the real number line has infinitely many numbers, right? And then the same thing goes for this, right? You know, they could pick, so let me just kind of highlight there, and let's say there. So anything in this region, there is, so like, again, so graphically what it means is, if you were to pick any y value and draw a horizontal line at that y value, if that horizontal line would always hit the graph of the function, then you could always find an x. So these three at the top here, yeah, they are ways that you could always end up losing this game. The reason why I would pick this one is if you stay within the range of the function, when I look at this here, right? And if I wanted to, right? In fact, if I wanted to, I could extend it even more like this, right? But the whole idea is now you pick any y value here and you try to draw a horizontal line, it will always hit the graph of the function at least one point, right? You know, so let's say you pick this y value here. So if you pick this as the y, then I would pick this as the x. If you picked, let's say, this as the y, then I would actually have several, not several, but I'd have a couple x's to choose from. So if this is like a y1, then I could pick that as my x1, or I could pick that as my x1. So yeah, any y that you pick here, right, I am guaranteed to find at least one x that would, when evaluated in my function, would give me the y that you picked, right? So can you see why these have the potential for you to lose, whereas this one you would always win? If you had to pick the x, you would always be able to find it. The difference between the top three and this one in the middle down here is continuity. As a reminder, this function has a removable discontinuity right at that point, right? This one has a jump discontinuity, right? This function has an infinite discontinuity, right? So when you have discontinuities, then the guarantee of being able to find an x value goes away. And what the intermediate value theorem, it essentially states that guarantee. So under certain conditions, you, as the person picking the x value, would always win, right? So let's state the the theorem, and then just do a couple quick examples to show you one way that this is used. And so here is the statement, right? So here's our theorem, and this is our beautiful IVT, and it seems like such an obvious theorem too, right? You know, if you avoid holes and jumps and vertical asymptotes, yeah, it's like everything's filled in. So if I draw a horizontal line, right, I'm always going to hit it at least one point. Well, it turns out the proof of this theorem is way beyond the scope of this particular course. It seems so obvious, but to prove it for every continuous function, yeah, not so easy. It's a fun proof though, but yes, it's very advanced. And so this is what it says. Let f of x be continuous, and that's the key here. It's got to be continuous on the interval, and this is going to be a closed interval, meaning the endpoints are included. So you might have, so I'll write it like this, right? So let f of x be continuous on this closed interval if y, and I'll use y0, right? Since so if y0 is any number between f of a and f of b, right? And you'll see the reason I say between and not necessarily use an inequality is I don't know if f of a is bigger than f of b or less than f of b. So I'm just saying if you were to pick any number between these y values, right? So if y0 is any number between these two y values, then there exists at least one x0 inside this interval, right? So one x value in our interval such that when I take my function and evaluate it at x0, I will get the desired y value, right? And that's what the IVT states, right? And now they don't always use like x0 and y0. Sometimes they use like a, well, not a, but they might use C and L, something like that. But I just wanted to specifically, you know, use the notation that we're used to when we think of the y values. We think of our range, and then when we think of our x values, it's the domain. So now the idea is for every y value in this range, there will be at least one x, right? Now, before we get to like a specific type of question, I just want to illustrate this theorem with a very familiar function. So I guess it is an example, but not like, you know, find or do, but mainly one that just illustrates this idea. So maybe we'll just list our examples like this, and then we can go ahead and start with this one that illustrates it, and then look at other ones where we're asked to do something specific. You know, when you think of your sine or cosine functions, right? And so here is, you know, one period of sine, and then, you know, it would go back basically like that, and so forth. Okay, so yeah, that's good. So let's say it goes like this, and we know what the range, right? So our function is our basic sine of x. A couple of things to note. The domain of this function is all real values of x, right? And the range is all values of y between plus or minus 1. That's what it oscillates here. Your basic sine function never goes higher than y equals 1. Oh, I did a mark there. And then it doesn't go any lower than y equals negative 1, right? And the thing is, so if I pick any number between plus or minus 1, and I draw a horizontal line, look at how many times it hits this trigonometric function, this periodic function. It hits it, in fact, infinitely many times. And that's why, like when you're solving trig equations, so for instance, let me say it like this. For y0 in this range, right? The equation sine of x equals y0 has infinitely many solutions. And that's why the theorem says at least one. You could have infinitely many, or you could just have one or two, but there has to be at least one x value that would satisfy that specific y. So it has infinitely many solutions for x0. So let's just say it has infinitely many solutions, right? And in trigonometry, you learn how to find all those solutions. Even though there are infinitely many of them, there are ways you can write it down. Now, if I were to pick something outside of this range, for instance, this horizontal line never hits the sine curve. And similarly, this horizontal line that's up here never hits the sine curve. You know, so for values of, so if you're y, right? So for y0 that's either bigger than 1 or for y0 that's less than negative 1, then that same equation that over here had infinitely many solutions now has no solution, right? There is no x that would correspond to, no real values of x. So this has no real solution. Right now, the reason I say real there is because if you go on and take more advanced classes in math and you study complex analysis, you realize that if you allow your domain value to be complex, then it turns out this equation now not just has solutions, but it has infinitely many complex valued solutions, right? So that's why I always put that little disclaimer there, right? Now, the interesting thing about this too is that this idea of, whether or not a horizontal line hits the graph of a function, that's actually related to another big problem in math, and that's related to the problem of finding a root or finding a zero, right? And the next example illustrates this, right? And it's not necessarily that we're going to find the root, but we're going to identify where there has to be a root. Okay, so here's our question. So it's kind of a proof question. So show that there is at least, let me fix this. Show that there is at least one root of the function 3x to the 7th minus 2x to the 5th plus x minus 1 in the interval 0, 1. Right? So that's what we have to show. So we have to show that this function has at least one root in this interval, right? Now, the thing is, this is a polynomial of degree 7th. Good luck trying to easily find the root. So if you're thinking that this is a question that's asking you to find the root, then you're misinterpreting the question. They just want us to argue, to give an argument, or to give an explanation as to why there has to be a root of this function between 0 and 1. And let's think about the root finding problem. So I'm just going to, before we get into the actual explanation, so the idea of a root is that you have your x-axis, and then the function is going to, touch or possibly cross the x-axis at some point. So as far as roots, they tend to look like this or like that. Even if it just touches, right, like that or like that, right? So each of these points are considered roots or zeros of the function, right? So those are your roots or zeros. Now, in certain cases, like these two, if you notice the function, think of your y-axis now. Think of your y-axis there. Then when the graph is above the x-axis, right, that corresponds to positive values of y, right? So all the y values here, so these are positive y values. And then as soon as it hits the 0 and then it goes down, then that's a negative y value, right? And then similarly here at this one, the function, as you go from left to right, the graph of the function changes from negative to positive, and then it hits it, right? So, but the thing is, you can't always just say, okay, if the function changes from positive to negative, because that's not true. Here's an example of a function where I will draw it so that it changes from positive to negative, but it will not have a root. So in other words, the function could do like this. What if it has a jump where it just decides to jump over the x-axis like this, right? Or what if it just happens to have a hole right at the x-axis? So like this type of function, like that, and then like that, right? So these functions do change from negative to positive, or I could have it going from positive to negative. But because of the discontinuity, it didn't have to actually pass or touch the x-axis, right? So you have to be careful. The other thing you have to be careful, and this goes back to important facts about polynomials in algebra, there are some polynomials that have roots of multiplicity, what we say greater than 1, right? And if your multiplicity is an even number like 2 or 4 or so forth, then yeah, you could have graphs of functions that look like this where it does have a root, but there is no sign change. It doesn't go from plus to minus or minus to plus, right? It stays the same. So with roots, you have to be careful. But what we can say for sure is this. If the function is continuous, right? So that would rule out these, because these are not continuous. So if the function is continuous and changes sign on the interval, so it goes from plus to minus or minus to plus, that rules out these too, right? Then the function would have to have at least one root, right? And that's what we can do here to explain why this function has to have an interval. So our argument has to do two things. It has to explain why we know that the function is continuous and Why do we know that there is a sign change? How do we know those things, right? So first, let's talk about continuity. And this goes back to what we said about some of our elementary functions, like polynomials, for instance. So this function is continuous for all real values of x, not just the interval 0 to 1, but this function, so f of x, is continuous, right, for all real values of x. So what this tells me is that the intermediate value theorem applies. I have a continuous function, I have a closed interval there, and if for instance, let's say I evaluate the function at 0. What do I get when I evaluate it at 0? So if I plug 0 in, looking at the operations, pretty easy. I'll have 0 minus 0 plus 0 minus 1. So I'll have a negative 1. And then what about at 1? What if I do f of 1? So f of 1 is equal to 3 minus 2 plus 1 minus 1. So that's equal to a positive 1. So look at what we have. We have a continuous function. We have a function that where at the left endpoint of this interval, it has a negative function value, so a negative y value. So it starts somewhere down here. And then at the right endpoint of the interval, if I plug 1 in, I get a positive 1. So it changes from negative to positive, and because it's continuous, it has to pass through the x-axis. So it has to have a root, right? So by the so let's now write our sentence explaining all that, because we're not just going to put this down and hope that the reader is going to like connect the dots for us. No, we have to connect the dots for the reader. We have to show all the calculus concepts that are related to this type of problem. So since f of x is continuous and changes sign, so and changes sign, not sine, so changes sign on the interval, 0 to 1 by the IVT, right? So by the IVT, there has to be at least one solution to this equation. So by the IVT, there is at least one x0 in the interval, so in the same interval, oh, I forgot a negative sign there, in the interval, such that when I plug it into my function, I have to get 0, right? And that's what we're essentially showing, right? So again, a lot of important things here. You know, obviously the concept of continuity, check. Then we have the algebra, where we evaluate it at the endpoints, and we get that sign change. And then invoking that powerful theorem, right? So using the IVT, it explains why this function has to have a root or a 0 between 0 and 1. At least one. It could be multiple ones. The function could do something like this, right? You know, here is your interval, 0 to 1. And we know that at 0, it's negative 1, so it starts somewhere down here. And then at 1, it's positive 1, so it's somewhere up here. But we don't know how many times it does this, right? We don't know how many times. Especially with polynomials of a high degree, that oscillate a lot. Now I'm not saying that it does, right? The fact is we don't know. But we can't say just one. We can't use the word exactly one or exactly two, but there has to be at least one point where the function crosses or touches the x-axis, because it could do something like this as well. Again, lots of strange things can happen with polynomials, but yeah, it could do this, then it could touch, and do other things like that, right? But yeah, so again, it would have multiple ones, but even if it touches it, we know that it has to do something at least like this or like this once in this interval because of continuity. Because once we start drawing and we have to go from this negative value to this negative value, I am not allowed to have holes or jumps or vertical asymptotes. So in that smooth continuous motion, by doing that, I have to cross the x-axis at some point, right? So that's one type of problem that's pretty common for the IVT, and we will see other problems going forward. So hopefully this one of our big theorems of calculus, it's easy for you to understand, and hopefully the few examples kind of illustrates how it can be used. And we'll see you in the next video.